Dive into the microscopic world and you'll find a realm where classical mechanics fail to explain the strange phenomena. This is a world where particles can exist in multiple places at once, where they can seemingly teleport through barriers, and where they can be entangled across vast distances. In this world, our familiar notions of space, time, and causality seem to be turned on their heads. Classical mechanics, the grand old theory that served us so well in understanding the macroscopic world, falls short when it comes to explaining these microscopic enigmas. It assumes a continuous and deterministic universe where everything is predictable if you know the initial conditions. But the microscopic world is anything but predictable. At the turn of the 20th century, scientists were grappling with two major problems that classical mechanics couldn't solve. The first was the blackbody radiation problem. Classical physics predicted that a blackbody, an idealized physical body that absorbs all incident electromagnetic radiation, should emit infinite energy, a prediction clearly at odds with reality. The second problem was the photoelectric effect, where electrons are emitted from a material's surface when light is shone on it. Classical theory suggested that the energy of the emitted electrons should depend on the intensity of the light, but experiments showed that it actually depended on the light's frequency. These problems perplexed scientists and led to a profound shift in our understanding of the universe. Max Planck, in a desperate attempt to solve the blackbody radiation problem, suggested that energy was not continuous, but came in discrete packets, which he called quanta. This was a radical departure from the continuous values of energy that classical physics held dear. Albert Einstein then applied this concept of quanta to the photoelectric effect, suggesting that light itself was made up of these discrete packets of energy, later called photons. These insights laid the groundwork for a new theory, quantum mechanics, that could explain the weird and wonderful world of the very small. This enigma gave birth to a revolutionary concept, quantization, a cornerstone of the quantum world. A concept that transformed our understanding of the universe and unleashed a technological revolution that continues to shape our world today. Unlike the classical world, properties like energy, momentum, and angular momentum become quantized in the quantum realm. This means that these properties can only take on specific, discrete values, much like the rungs of a ladder. This is a significant departure from the classical perspective, where such properties can take on any value in a continuous range. Take the example of energy levels in atoms. In a hydrogen atom, the electron doesn't exist at any arbitrary energy level. Instead, it occupies certain distinct energy states, or orbits. This stepping of energy is a fundamental characteristic of quantum systems, leading to the concept of quantum leaps. But what about momentum and angular momentum? Well, they too follow suit. In atomic and nuclear physics, both linear and angular momentum are quantized, leading to the existence of specific, discrete states. Now, let's take a moment to talk about wave-particle duality, a cornerstone of quantum physics. This concept suggests that every particle also possesses wave-like properties and vice versa. A classic example is light, which exhibits both particle-like and wave-like behavior. So how does this relate to quantization? Well, it's the wave-like nature of particles that gives rise to quantization. When particles are described as waves, their properties become quantized due to the wave's inherent discreteness. For example, an electron in an atom can be represented as a standing wave, a wave that doesn't travel but oscillates in place. The electron's energy levels correspond to the distinct vibrational modes of this standing wave, which are quantized. The concept of quantization also extends to more exotic systems, like the vibrational modes in molecules or the quantum states of light, known as photons. These systems too exhibit quantized properties, further cementing the universality of quantization in the quantum world. In the quantum world, particles take leaps rather than smooth transitions, leading to the fascinating phenomenon of wave-particle duality. The mathematics of quantum mechanics, with wave functions and the Schrodinger equation, encapsulates the principle of quantization. Diving into the heart of quantum mechanics, we encounter the concept of wave functions. These mathematical functions are not just abstract symbols, They hold the keys to understanding the behavior of quantum particles. Wave functions describe the state of a quantum system, encapsulating information about a particle's possible positions, momenta, energies, and other properties. They provide a probabilistic view of the quantum world, where certainty gives way to a web of possibilities. This probabilistic nature is brought to life by the Born rule, which tells us that the square of the absolute value of the wave function gives the probability density of finding the particle in a particular state. In essence, the wave function paints a picture of where a particle might be and what it might be doing, but it doesn't tell us for sure until we make a measurement. Now, let's turn our attention towards the Schrodinger equation, the cornerstone of quantum mechanics. Named after Erwin Schrodinger, this equation is a mathematical expression that describes how wave functions evolve over time. It's like a recipe for predicting the future states of a quantum system. The Schrodinger equation incorporates the principle of quantization. It allows us to calculate the discrete energy levels of quantum systems, such as atoms and molecules. This equation, when coupled with the concept of wave functions, provides an elegant mathematical framework for understanding the quantized nature of the microscopic world. Let's not forget about operators, key players in the mathematical formalism of quantum mechanics. In the quantum realm, physical quantities like energy and momentum are represented by operators. These mathematical entities act on wave functions to extract information about the observable properties of a quantum system. Operators play a crucial role in making predictions and performing calculations in quantum mechanics. The complex mathematical formalism of quantum mechanics beautifully captures the quantized nature of the microscopic world. The principle of quantization provides an explanation for phenomena that were once baffling. It's like finding a key to a lock that's kept us puzzled for centuries. One of the most striking examples of this is the explanation of atomic spectra. Atomic spectra, you see, are fingerprints of elements. Each element produces a unique set of lines, or spectra, when its atoms are excited and then relax. Prior to quantum mechanics, these spectral lines were a mystery, but through the lens of quantization, they make perfect sense. The distinct lines correspond to the precise energy differences between the quantized energy levels of the atoms. When an electron transitions between these levels, it either absorbs or emits energy in the form of light, the color of which corresponds to these energy differences. This brings us to another significant implication of quantization, the concept of photons. These are the discrete packets of light energy, the quanta of the electromagnetic field. They're not continuous waves, but individual particles, each carrying a specific amount of energy. This wave-particle duality of light, where it behaves as both a wave and a particle, further validates the principles of quantization. But the reach of quantization extends far beyond atomic spectra and photons. It permeates almost every corner of modern technology. Take the quantum theory of solids, for instance. It explains properties of solids like electrical conductivity and heat capacity, which are otherwise inexplicable in classical physics. It's the foundation of semiconductors, those tiny devices that are the building blocks of all modern electronic gadgets. And let's not forget lasers. The very principle of lasers is based on stimulated emission, a process where an excited atom is stimulated to emit light of a particular wavelength, which is again a direct consequence of energy quantization. Transistors, too, are a product of quantum mechanics and quantization. They're the switches that form the basis of digital electronics, enabling us to develop computers, smartphones, and all the technological marvels we see today. Quantization, thus, plays a pivotal role in our understanding and advancements in modern technology. Taking the concept of quantization further leads us to advanced principles like canonical quantization, second quantization, and the uncertainty principle. Let's start with canonical quantization. This is a formal procedure for transitioning from classical to quantum mechanics. It's like crossing a bridge from the world of the large and visible to the world of the small and invisible. In canonical quantization, classical variables are replaced with quantum operators, and Poisson brackets are replaced with commutators. This lays the groundwork for the quantum description of a system. Next, we have second quantization, which is a bit of a misnomer. It doesn't mean quantizing something twice, Rather, it's about describing systems with variable particle numbers. Second quantization gives us the tools to describe phenomena like particle creation and annihilation, which are central to fields like quantum field theory and many-body physics. Finally, we come to the uncertainty principle. This principle is a fundamental aspect of quantum mechanics, and it tells us that we can't know both the position and momentum of a particle with absolute precision. The more precisely one measures one quantity, the less precisely the other can be known. This isn't due to any limitation in our measurement devices, but a fundamental aspect of nature itself. It's like trying to watch a movie and read the script at the same time. You can't fully focus on both. But don't let the name uncertainty principle mislead you. Although it introduces a certain level of unpredictability, it's this very principle that gives rise to the structure and stability in the quantum world. Despite its name, the uncertainty principle is actually a source of certainty in quantum mechanics. Each of these concepts take us a step deeper into the fascinating world of quantum mechanics.